Welcome back, class. Over the past number of weeks, we have looked at how we can take any real number, whether it be a whole number, whether it be a fraction, whether it be a negative number, and we can add those real numbers in any order. We also know that we can multiply those real numbers in any order. We call that the commutative law. We know that not only can we add and multiply numbers in any order, but that real numbers also obey what is known as the associative law. So if we have a equation or an expression, we know that as long as the numbers that are contained within the expression are added together, or they're all being multiplied with one another, we can move around or entirely remove a sequence of parentheses in order to evaluate that expression. Next, we introduce this idea that there also exists an inverse law. That is a very special property of real numbers. The inverse law says that if you take any real number and you multiply it by its multiplicative inverse, you will always get 1. Additionally, the inverse law says that if you add the additive inverse to a real number, you will always get 0. The identity law is equally special, although it seems trivial at first. It says that if you take a real number and multiply by 1, you always get the original number back. And if you take a real number and add with 0, you always get the original number back. It turns out that with the commutative, associative, inverse, and identity law, along with the special instance, the special case of the distribution law, in addition to a number of special properties of equations, we can manipulate any equation regardless of how complicated that equation happens to be, which is great. So if we're analyzing, say, a physical system, and we have an equation to represent the behavior of that system, we know that we can use the rules of algebra in order to perform manipulations on the equation, in order to perhaps be able to discover some sort of interesting new properties about the system we might be analyzing. Now, before we get to equations and how we might use the rules of algebra to manipulate equations, let's just introduce or perhaps reintroduce the idea that there are certain properties of equations that we should be all familiar with. One of the properties of equations that we should all be familiar with is known as the additive equivalence principle or the additive equivalence property. And it says that if you have an equation, such as the one shown here where I have x is equal to 1, you may add a value on both sides of the expression without changing the value of the actual equation itself. And so in this case, the equation is representing that we have an unknown number, and the value of that unknown number is equal to 1. If I was to, say, add 2 to both sides of the equation, on the left side of the equal sign, I will be left with x plus 2. On the right side of the equal sign, I will be left with 1 plus 2, which gives me 3. And what the additive equivalence law is saying, it's saying that your value of x didn't change just because you decided to add 2 on both sides. Instead, we now have a new equation with the value of x, which is preserved. Okay? And in fact, you can determine this to be true because if you knew that in this instance, your unknown number, or x, was equal to 1, and you had some expression x plus 2 is equal to 3, if you were to plug in the value of x, you could check to see that the equation was still imbalanced. Rather. You would have 1 plus 2 on the left-hand side, and you would then check to see if that equals 3, which is the quantity on your right-hand side. And because you were able to obtain 3 is equal to 3, it essentially tells you that the equation wasn't broken just because you decided to add 2 on both sides. Now, another property of equations is called the multiplicative equivalence law. And what it says is that you can multiply a value on both sides of an equation, and the equation itself won't break, as long as you're being careful with how you perform that multiplication process. So for example, if I have an equation, let's go back to our original equation, x is equal to 1, and we decide to maybe multiply 2 on both sides of this equation, as you see here. Well, on my left side of the equation, I would be left with 2x. And on the right side of my equal sign, I'd have 2 times 1, or 2. My original equation, of course, just reads an unknown number is equal to 1. This second equation that I've produced by multiplying 2 on both sides says 2 times an unknown number is equal to 2. Well, reason dictates that 2 times an unknown number is equal to 2. The only number that suffices would be 1. The only number that this unknown number could possibly be, said another way, has to be 1 in order for this equation to be preserved. And in fact, that's the case. Now, we do have to be careful because while it is true that when you multiply both sides of an equation, the equation itself will be preserved as long as you've multiplied the same value on both sides. How you do that is critically important. If instead of x is equal to 1, you had an equation or expression such as x plus 2 is equal to 3, you cannot simply multiply 2 with your x value and maintain the same value of x. Because what's going to happen here in this particular equation is that for this equation, it reads an unknown number plus 2 is equal to 3. Here, reason would suggest that the only value that could suffice for our unknown number would be 1. And you could check this by just looking and seeing that 1 plus 2, ask yourself, does that equal to 3? And if you get 3 is equal to 3, then that means you found the value of x that suffices. But what happens if you're not careful with the multiplicative rule is if you had, say, multiplied both sides of the equation by 2, and maybe on the right-hand side of the equation you multiplied the 3 by 2, and on the left-hand side you multiplied 2 only by the x, then what's going to happen is your x value actually won't be preserved because you're going to have an entirely new equation which doesn't represent the properties of your previous equation. Said another way. And in this case, your equation reads 2 times an unknown number plus 2 is equal to 6. Well, the original equation had the unknown number equal to 1. So if you were to substitute in the original unknown number from your first equation into your x value, what would happen is you have 2 times 1, which is 2, and 2 plus 2 gives you 4, and 4 does not equal 6. So, of course, students at this moment in time will get confused. They said, well, we were able to multiply on both sides here, and we were able to preserve the value of x. But when we multiplied 2 on both sides here, we weren't able to preserve the value of x. So what's going on? Well, it turns out that in order to preserve the value of x, we actually have to follow the rules of algebra when we're multiplying on both sides. So it is true, we can multiply by 2 on both sides, but what's critically important to recognize is that the left side of the equation isn't just x, it's x plus 2. Okay, so you have to multiply 2 by the entire chunk on the left-hand side of the equal sign. And similarly, you'd have to multiply 2 by whatever is on the right-hand side of your equal sign. And so now you have a distribution law case where you've got a number that's parked out inside of a sequence of parentheses. So you'd have to distribute the number to each value in the parentheses. So you'd have 2 times x plus 2 times 2 is equal to 2 times 3. Now, if you do this, you're going to get a better answer. You're going to get 2 times an unknown number plus 4 is equal to 6. Because we knew that the original value of x was 1, since the only unknown number plus 2 that's equal to 3 happens to be 1, you can go ahead and check this by plugging 1 in for x and determining whether or not 2 times 1 plus 4 is equal to 6. Well, 2 times 1 is 2, plus 4 does indeed give you 6. So the real issue with our previous problem was that we were not following the distribution law. Okay, so if you have a number of terms on the left-hand side or on the right-hand side, you have to remember to use the distribution law if you should multiply a value on both sides of your equal sign. With that knowledge in hand, we can now shift our attention to solving what are known as linear equations of one variable. You'll often hear me refer to linear equations of one variable as LEOVs. LEOVs are special types of linear equations that are the most basic linear equations that you are dealing with in a given algebra class. So if you recall back to your 5th grade class or your 4th grade class, at some point in your life, if you took an American public education, you would have encountered a problem where you've got a box plus a number is equal to something else. And you'll often be asked a question, what goes in the box? And of course, students who remember these problems will say, well, 5 goes in the box because only 5 plus 5 is equal to 10. And at some point in time, they transitioned away from giving you problems with a box, and they said, okay, well, now we have a number that's represented by a letter that we call a variable. The variable just says, it just means an unknown number. So we can replace the box with the letter x, and we can rewrite this equation as x plus 5 is equal to 10. Then at some point in time, your teachers may have taught you that in order to solve this problem, because you have x plus 5 is equal to 10, and the opposite of addition is subtraction, you needed to subtract 5 on both sides in order to solve this problem. The problem is students will often get confused as to whether they need to perform subtraction on both sides, whether they need to perform addition on both sides, multiplication on both sides, and or division on both sides. And so the student who's looking for a very easy answer will often get confused by these operations, okay? And in that student's defense, part of the issue is that subtraction is not an algebraic operation. And so if you're dealing with an algebra as the subject, which is what this class is about, you want to make sure that every single operation that you're doing, that you're performing in order to manipulate a given equation actually follows the rules of algebra. So we need to fix this. Instead of saying that we're going to subtract 5 on both sides because subtraction is the opposite of addition, we're going to use the additive inverse law on both sides. The additive inverse of a positive 5 will be a negative 5. And according to the additive inverse law, if you add negative 5 with 5, you will get 0, which is beautiful. Now, we know because of the additive equivalence law that we could add any number to both sides of our equation. We know that. That's the additive equivalence property of equations. Okay, so look back at this reference just so you understand and are clear that it is, in fact, proper to do this. So I know that I could add 1 on both sides if I wanted to. I could add 3 on both sides. I made the choice to add negative 5 on both sides because negative 5 is the additive inverse of 5. And what's beautiful about doing this is that on your right-hand side of the equation, you've got a positive and minus, which we know is just a subtraction operation. So now you have 10 minus 5 gives you 5. X plus 0, according to the identity law, will just be x. We don't have to waste brain cells on that operation. So this last law, we use the identity, or that last operation, we use the identity law, rather. For this second to last operation, we use the inverse law. And so in 2 steps, we were able to obtain our answer, x is equal to 5. Now, of course, students will say, Mr. B, why are we using all of these extra steps? Isn't it an extra step to remember that we're actually using an additive inverse instead of subtracting on both sides? I would tell that student this is true. It is going to take you a little bit more time and conscientiousness to add an inverse on both sides. However, I would also tell that student that what we're doing is not only algebraically correct, but this process, this procedure, this idea of being able to use the additive inverse when we please inside the context of solving an equation is going to help us out when we get to chapter 5, when we get to chapter 6, and in fact, whenever you go to the next class, Math 1100, and get hit with chapter 8 and 9 in Math 1100, which are pretty difficult sections. So we're going to need to understand the idea, the concept of using the additive inverse, and understand that that's what's happening when you subtract on both sides. And we need to force ourselves to understand this using repetition, which is why we're going to write out all of our steps. Now, it turns out that this is a special type of linear equation of one variable, or LEOV, and we call this a one-step LEOV under addition. So this is an additive case of a linear equation of one variable. There are, of course, other types of linear equations of one variable. There is the one-step LEOV under multiplication. If we had, say, 5 times an unknown number is equal to 25, students will often recall their professors or their instructors in previous classes telling them to do division on both sides or some similar operation in order to obtain an answer. Okay. In this class, however, we have to use the rules of algebra in order to obtain a solution to any equation. And so what we're going to do is we are going to use the multiplicative equivalence rule, or the multiplicative equivalence property, knowing that we can maintain the balance of an equation by multiplying a value on both sides. We get to choose the value, and we're going to use this multiplicative equivalence law along with the inverse law, specifically the multiplicative inverse law. We're going to take this 5 and multiply by its inverse. It turns out the inverse of a number is just that number flipped underneath a fraction. Said another way, it is the reciprocal of a number. A reciprocal of a number is always the multiplicative inverse of that value. So in this case, if you have 5, flipping 5 will allow you to find the multiplicative inverse. If I had, say, 3 halves, and I wanted to find the multiplicative inverse of 3 halves, I just flip the values. So flip the fraction in that instance. If you had negative 4/5, same thing. Even with negative numbers, you just flip the values around. But with negative numbers, you definitely need a negative number as well. So flipping the fraction or flipping a number to find its inverse doesn't remove the negative symbol. From your inverse of a negative will have a negative as well. At any rate, going back to this equation, if you multiply 1/5 by 5, this will give you 5 over 5x. And multiplying 1/5 by 25 gives you 25 over 5. 5 divided by 5 just gives you 1 because of the inverse law. And on the other side, you get the traditional setup, division setup that you remember from your high school classes. And so 25 divided by 5, that's going to give you 5. 1 times x is just x, and voila, we have our answer. Okay, students will, of course, say, this is a lot more work, maybe. It's more challenging for me to think in terms of multiplying by a fraction than it is for me to just think about division on both sides. But it's important for us to use this multiplicative inverse law as opposed to division on both sides, because that's going to help us out going into, again, chapter 4 next semester, chapter 5 this semester, chapter 6 this semester, and especially chapter 8 and 9 next semester. So we're going to really, really want to have a command of this specific law. Just to review, you went from your original equation using the multiplicative equivalence property, multiply on both sides with the multiplicative inverse of the number that's in front of your x. That is the inverse law step of your problem. Then you're exploiting the identity law, the multiplicative identity, which says that if you take a number and multiply it by 1, you get the original number back. So you don't have to know what x is. If you multiply 1 with x, it always is going to give you x. Again, we usually skip over the identity law step in most textbooks. And so we would call this a one-step LEOV because you only needed to use the inverse law, the multiplicative inverse law, in order to solve this particular problem. In general, a one-step LEOV under addition will look like the following. You'll have x plus some number is equal to something else. And under the addition case, you're going to use the additive inverse of whatever number is being added with your x. And you're going to use the additive inverse on both sides. Then what happens is your numbers will add together to be 0 on the left-hand side. So whatever value is being added to x, that value is going to add to 0 on the left-hand side. And of course, we know that x plus 0 is just x because of the identity law. But on your right-hand side, you'll have b plus a negative a, which is the same thing as b minus a. So we know now that we have a general procedure by which we can go from a LEOV one-step under addition to its solution by simply using the additive inverse. The same is true for an LEOV one-step problem statement under multiplication. A LEOV one-step problem statement will always have the following form. You'll usually have some number that's in front of your variable. That number is called a coefficient. So you'll have a coefficient in front of your variable. This a, that's the coefficient. And this will be equal to something else on the other side of your equal sign. I don't know what b is. You don't know what b is. B is just some number. A is just some number. These can be any numbers we want them to be. But what we know is that if we take the multiplicative inverse of a and we multiply the multiplicative inverse on both sides, and here, let me use two different colors just so that you can maybe see that a little bit better. Take the multiplicative inverse, you multiply it on both sides. What's going to happen is on the right-hand side, you just have the multiplicative, the multiplication with fractions rule. So you have 1 over a times b, which b will just multiply with 1, and you'll now be left with a new fraction, b divided by a. Because we don't know what b is and we don't know what a is, that's pretty much all we can do. But what's interesting is on the right side of your equation, sorry, on the left side of your equation, rather, you've got a times its inverse, which we know is just a over a. And so everything's going to divide out. You'll have a divided by itself, which is 1. And 1 times x is just x. So you'll have x is equal to b over a. So we know that regardless of the numbers in front of your x, regardless of the values on the other side of the equal sign, for a LEOV one-step problem statement under multiplication, we are always able to use the following process in order to obtain the answer. You're going to use the multiplicative inverse law. That's the first step. Reduce your terms using the identity law. And then finally, you'll be left with an answer. X is equal to something else. Now, the next most complicated linear equation is going to be the linear equation of one variable two-step problem statement. These are going to pop up over and over and over again throughout your entire time in mathematics, all the way through college algebra, all the way through calculus, all the way through your engineering school if you take engineering classes, all the way through physics if you take physics classes, all the way through chemistry if you take chemistry classes, so on and so forth. So it behooves you to really, really, really learn this content okay? Because if you're a chemistry student, physics student, engineering student, comp sci student, this is going to pay dividends right here. This is the meat of the lesson. An LEOV two-step problem statement is as follows. You will usually have some sort of a setup like 5 times an unknown number plus something is equal to something else. Maybe we have 5 times x x plus 1 is equal to 10. The way in which we approach a two-step problem statement is we are going to use our additive inverse first in order to clear off a number that's either being added or subtracted from some unknown value, some variable that we would like to solve for. So if this problem statement asked us to solve for the unknown number, solve for the variable x, solve this equation, okay, what we're going to try to do is we'll use that additive inverse first. We'll add, in this case, because we have a a positive 1 being added to 5x, we'll add a negative 1 on both sides of our equal sign, knowing that the additive equivalence principle will hold here because we have an equation and we're just going to add a number, a real number, to both sides of our equation. The additive principle of equations will hold. And that's good because if we add a negative 1 on both sides, the additive inverse law will kick in. You have a positive 1 and a negative 1 added together. We know that's going to be 0. We don't even have to waste brain cells on this. Then on the right side of your equal sign, you've got 10 plus a negative 1. Well, that's going to be 10 minus 1. 5x plus nothing is just going to give you 5x because of the identity law. There again, we don't have to waste brain cells, just automatically know 0 added to anything is just that something. And you have 10 minus 1, which is 9. The interesting thing here is now you are left with a one-step LEOV. And in this instance, we were left with a one-step multiplicative case LEOV, right? So we already know how we can solve a one-step multiplicative case. We are going to go ahead and multiply the multiplicative inverse of the coefficient that's in front of x. 5 is the coefficient for x. 5 is the number in front of my x. And we know that the inverse of 5 will be 1 over 5. Just flip the number. So if I multiply 1 over 5, the multiplicative inverse of 5, on both sides of my equal sign, what's going to happen here is you've got the multiplicative inverse set up on the left-hand side. You've got 5 times 1/5. That just gives you 5 over 5x. X doesn't change, okay? X is always just staying x for these types of problems. And on your right-hand side, you've got 9 times 1 over 5, which is just going to give you 9 over 5. 5 divided by 5 is 1. And 1 times x is just x. So you've got x is equal to 9 over 5. Cool? Cool. Now, in this particular problem statement, we had a specific sequence of values. We had 5 as the coefficient in front of our x. We were adding 1 to the 5x. And then on the right side of our equal sign, we had 10. And often students will just start memorizing how you solve this particular problem statement. And then when they go off on their own problem statement and they're faced with other numbers, then they start second guessing themselves. They start saying, well, am I doing things the right way? What's going on here? How do I solve this problem? And all we need to know is that for two-step problem statements, we can always find our unknown variable. We can always locate our x using the following process. For a two-step LEOV, you're always going to have an equation. Some number times x plus or minus something is equal to something else. Now note in this equation, I have a plus symbol, but b could be negative. B could be any real number. B could even be a fraction, okay? Because fractions are real numbers. Negative numbers are real numbers. So a, b, and c could be any real numbers that we're working with, and this particular process is gonna work for us. It's gonna allow us to solve the equation. If we want to start with solving two-step LEOVs, what we need to do is we need to add the additive inverse of whatever's being added or subtracted from your a times x value. And you're going to do that on both sides of your equal sign. Now, while we don't know what b is, I don't know what b is, you don't know what b is, I don't know what a is, you don't know what a is, I don't know what c is, you don't know what c is. What we do know is that the rules of algebra will kick in. In this instance, whatever b happens to be, it's going to be adding with its inverse. And so we don't have to waste brain cells. We know this is a additive inverse law case here. This will add to 0. And on the other side of our equal sign, even though I don't know what c is, I don't know what b is, you don't know what c is, you don't know what b is, we have c plus a negative b, which we know is the same thing as c minus b. Moving back to the left-hand side of our equation, we have a number times x plus 0 is equal to c minus b. Anything added with 0 is just that something. And so we will be left with a times x is equal to c minus b. At this point, you'll note that we have reduced a 2-step LEOV to a 1-step LEOV. This is the general pattern that you need to look for as you're solving these various linear equation of one variable problem statements. You always want to take a more complicated LEOV and reduce it to its less complicated form. Once we have a 1-step LEOV, in this case, we know that this is a multiplicative 1-step LEOV. We may solve the 1-step LEOV either using an additive or a multiplicative inverse. In this case, because we have a multiplicative 1-step LEOV, we will multiply using the multiplicative inverse on both sides of our equation. We'll multiply 1 over a on the left-hand side and 1 over a on the right-hand side of our equal sign. And what that's going to do for us is we will be left with a solution. In this case, we will know that x will equal c minus b all over a. Again, we don't know what c is, we don't know what b is, we don't know what a is, but this has to be the solution to this problem statement. It has to be. There can be nothing else because all we've done from one step to the next is follow the rules of algebra diligently. And we know that because we're assuming all of these numbers that we're dealing with are real numbers, and we know those real numbers themselves obey the rules of algebra, this should then be our specific answer. Now, it turns out that the pattern for solving more complicated problem statements is simply going to be an extension on this general principle. You're going to, for the more complicated cases, and we'll talk about that next lesson, you're going to be given a multi-step LEOV, and what you're going to want to do is you're going to want to reduce that to a 2-step LEOV. From a 2-step LEOV, we will reduce it to a 1-step LEOV, which we know will either be a multiplicative or additive case. And then depending on whether it's a multiplicative or additive case, we will use a multiplicative or additive inverse in order to obtain our solution. So the flow diagram, the general strategy for solving a linear equation of one variable is always as follows. It doesn't matter how many steps we might have for a multi-step LEOV. We may be given an incredibly complicated problem statement. We're going to use one rule of algebra at a time in order to eventually finesse the multi-step LEOV to a 2-step LEOV. In front of a 2-step LEOV, we know that the general solution will be to attack the number being added or subtracted from your x value, from your unknown number value on both sides of the equation, to then reduce the 2-step LEOV to a 1-step LEOV. Finally, you'll be left with your solution, and all is well. That's all I've got for you guys. I'll see you in class.